Good afternoon. Thank you for watching. Thank you for liking. We are looking here at a good video here, the volume of a pipe, the lumen and the sheath. We're talking about here a pipe which could very well be any type of pipe you might be thinking in your mind, a water line pipe, a gasoline line pipe, any material pipe which is used to channel a fluid or some sort of material from one point to another, and the channel right there is represented by means of your pipe. We're looking at the volume perspective of that. You know, if you are to draw a pipe over here three-dimensionally, I'll try to do this in a good diagram. I hope I do it. My drawing is a little weak. Anyhow, if you bring this down over here and then you bring it across and then you do this three-dimensional representation right over here, we're looking here at a very short pipe, but it indeed is a pipe. There are two parts to this pipe. From right over here to right here, you have what is called the lumen. The lumen is basically the channel, the volume, the internal volume which will transport the liquid, the fluid, whatever it is. And then you are looking at the sheath. The sheath can also be considered here as the layer of your pipe, or the solid portion of your pipe, the casing of your pipe. We can even call it right here the casing. This is all the external material which constructs the pipe. And you know, with regards to your sheath and your casing, you're looking at this part right over here, and that right there is your circumferential casing, your layering, your sheath which constructs the pipe. With regards to application and with regards to construction and manufacturing, this has big implications. The larger the internal diameter or the lumen of this pipe, the larger has to be the circumference of this entire pipe. The more materials are involved, the more layers are involved in constructing the pipe. So as you can see, with regards to the materials, the solids, the cost of constructing a pipe goes up as a lumen becomes larger. Anyhow, you have also the volume applications which come into play. As a lumen gets larger or smaller, you can transport less. And then you also have the effect of the pressure which comes in, how the pressure gradients change with the size or the volume of this lumen. You know, with regards to volume, anything which has space or anything which occupies space, for that you can calculate a volume. If you think about this pipe from a very basic perspective, you can do two volumes. You can do the volume of the lumen, which is how much liquid can be transported, and that would be the volume of that lumen, the inner volume. And then you can also do the volume of the solid portion of this pipe, which I'm calling here, as you know, the sheath or the casing of that pipe. Both of these, as you know, have practical implications. I've only hinted towards those, but our lesson here is on how you can do the volume determinations of these two items. If you think about it again, with regards to the lumen, it would very well be a cylinder. The lumen here looks very much like a cylinder. So if you know the volume of a cylinder is equal to pi r squared h, that very well gives you the volume, the lumen volume of your pipe. But we want to derive this using the terminology and everything which will come into play for a pipe. We're not talking about cylinders. It's just by coincidence the volume of a cylinder equals the volume of a lumen. But forget this part. This is just some background information only. How can we go about doing the determination of the lumen volume and the solid portion volume? We will do the solid portion volume first, then we'll show you the lumen volume. For that same pipe, let's look at the solid portion of the pipe, which I'm calling here the sheath or the casing or the layering of that pipe. You can do everything over here with regards to rotation of curves. If you have an x and y axis, you draw one vertical line that is x equals a, you draw another vertical line and that can be x equals b. The thickness of your pipe based on the amount of materials or the volume of the transporting items will very well be dependent on what is being transported. Something very thin will be weak, it will have less integrity, versus something very thick which will have more integrity, more strength, more rigidity, but then it will also cost more to manufacture because more materials are involved. Anyhow, we're looking here at a finite pipe. If everything over here is with regards to x equals a and x equals b, this right here represents the thickness of the pipe. The pipe materials which will go all around, this right here is the thickness. Our line of rotation is basically the y-axis. You know, when you're looking at the y-axis, you're doing a volume with respect to y. You're looking at limits here from a lower to a higher, but along the y-axis, along a vertical axis, and you're doing some sort of area integration with respect to dy. All of this seems complex, but it's actually very easy. Here we are looking at everything here with regards to equations which must be in the x equals format, and they are x equals a and x equals b very well fits this item we need over here. We have basically here two lines which will lead to two radii. We'll have an inner radius, we'll have an outer radius develop. From your line of rotation to the first line will be your inner radius, and that happens to be A. X equals A represents that, the radius right here. The outer radius is from your line of rotation to the next line, which is X equals B. From an inner radius, we end up getting an inner area, and everything here is always with regards to circular cross sections, whether they're discs or washers. Everything here is with regards to a circular cross section, and areas are always for circles, pi r square, and here you left pi a square, here you left pi b square. Now we have to determine what it is with regards to C and D. We're looking at everything here from 0 going up to a certain length of the pipe, which is height h. Our volume integral, which is not hard to develop, will become this. It'll always be in terms of this component here, the area, outer area minus inner area, because we have what will develop in terms of a cross section, a washer. When you have a washer, you have to look at inner and outer area, inner and outer radii, and that right there is why you have this. You're looking here from a lower limit of 0 to an upper limit h, height, which will determine how long this pipe might be, this plastic pipe, this metal pipe, whatever polymer pipe it might be. Outer area minus inner area, we have a b squared, that's outer area with the pi having been isolated and pushed out, minus your inner area dy. This is not hard. You're looking at everything here with regards to integrating with the y variable. You can do b square minus a square, and with that you can bring in this y. That right there is your antiderivative, which has come in by means of this integration procedure from an upper h to a lower 0. This b square minus a square could very well have been pushed outside as a constant if you wanted, or a coefficient, and then you would have a y with an h0. I wouldn't use the word constant, it's a coefficient, because this right here are variables which can change based on how thick you want to make your pipe. Anyhow, when you do this, what do you end up getting? You get a h and a 0. H comes in, 0 is meaningless. You get a b square minus a square with a pi, and then you have an h. This right here represents the volume of the solid portion of this pipe, the sheath of the pipe, or the casing of the pipe. This right here will also determine, based on the thickness of B and A, how much material will be used and how much a pipe of this certain dimension will cost. But if someone were to ask you what is the volume formula for a solid portion of a pipe, the sheath, the case, or the layering of the pipe, you could very well provide this, and it would be a good representation of that pipe. It looks and it mirrors very much the volume of a cylinder, pi r squared h. You have a pi, you have an h, which is shared here. The only difference here is you have a b square minus a square here. You don't have a b square minus a square in a cylinder, because a cylinder represents a complete through and through solid. This is not a through and through solid, because you have a lot of empty space, which is the lumen of the pipe. Anyhow, the volume of the solid portion of the pipe, the sheath, has been determined, and this right here is the formula that I'm happy with. I want to show you next the determination of the volume of a lumen. You know, the volume lumen will very much mirror exactly the volume of a cylinder, but we want to do it with regards to our terminology that we have over here. There isn't much that will change with regards to your presentation, but when you're looking at the volume of a lumen, you're looking at only the internal aspect. All we can do very well is just focus in only on this inner line, x equals a. When you reflect it on the other side, you have something like that. By means of that rotational around the y-axis, you end up getting what is called a cylinder. That cylinder would very well represent what the volume of that lumen would be. Here, in terms of the radius, you're looking at basically your radius, which is the distance from your line of rotation to the very first line, or the curve. You want to call it a curve, you can. It's a. But here you don't have a washer, you very well have a disc. A disc having a certain radius, which is a, and it has a certain area, pi r square, which is pi a square. This pi a square represents your area with respect to y, which here is pi a square. You have to integrate this again from 0 all the way up to h. Your volume integral is not hard. You can push the pi out. You're looking from 0 to h, a square dy. You can push that a square out with the pi, and you're looking from 0 to h dy, and you have pi a square. The antiderivative of dy is just a y from an upper h and a 0 lower limit. 0 is meaningless. When you do the definite integration, you have a pi a squared h. This right here is your volume of your lumen, which very well mirrors the volume of a cylinder, pi r squared h. The only difference here is you're looking at a radius square, here you're looking at a square, but the a square is the same as the radius, except we're using different terminology. So if someone were to ask you what's the volume of a pipe's lumen, it's no different than the volume of the cylinder. You could very well fit snugly into that inside of that pipe. The lumen of the pipe is very well the same as the volume of a cylinder. Just right here is your volume of a pipe's lumen, and it determines the amount of volume or the liquid or the materials you can push through a pipe. In this video we have looked at the volume of a pipe in terms of its lumen, the internal volume, and the sheath or the casing or the layering of the pipe, the solid portion of a pipe. And I hope you found this material presented in this video relevant and practical. Thank you for watching. Have a nice day.